how has been COVID? How has it been in Bandung?
Bandung relatively okay. So we already announced it is in the we define from blue, green, and red. So we are now is already in the blue zone.
Oh, excellent.
Yeah, but
excellent.
Jakarta is still red, probably still black. So the worst one is black.
Oh, okay.
Yeah, Bandung is relatively okay, although it's still
Okay.
we have to be cautious,
Yeah.
and then but I'm still staying at home so that all the classes is still not yet started the classes.
Right.
So the semester will start on August.
Right.
In August.
Okay.
In August.
When is your final of your year? Is it in November, December, or is it?
The end of the semester is May. So that starting of the semester is like in United States. So that are starting on the August or September, August, and then that one is the first semester, and then second semester is started on January until May. So now it's a summer break.
Right.
Although we don't have summer. So your class already started in the university?
Well, they've been lecturing by Zoom for a long time.
Oh, yeah.
And they'll be starting. 1/3 of the students are allowed to come back to the university from today, from this week.
Yeah. But Sarah, you have to say something before starting. Sarah, please.
Okay, Pak. Thank you. And sorry, Pak Chandra, for this session. I like to introduce Adina as a host for this session. Adina, can you hear me?
Yes, can my voice be heard, Saras, Professor Chandra, and Professor Buckley? Yeah. So since the time is already showing 1 p.m. Jakarta time, let me introduce myself first. My name is Adina from PSLH ITB, and for this session, we will be having a lecture held by Professor Chris Buckley. So for today's session, Professor Buckley will be giving a lecture with the title Appropriate Technologies for Wastewater Treatment in Developing Countries. And for this session, Professor Chandra will act as a moderator during the lecture, which will be held for like to share Professor Buckley's short CV resume. Excuse me, I would like to share screen. Yes, perhaps for Professor Chandra, you may begin the session now. Thank you.
Okay. Good morning, Chris.
So, good morning.
We are here is already afternoon. So good afternoon, everybody. So in Indonesia, it's already afternoon or maybe late afternoon for someone in the eastern part of Indonesia. So I'm delighted to introduce Professor Chris Buckley. So I know Chris, I think so more than, I think so it's almost 20 years, could be. So Professor Chris is the head of the Pollution Research Group in the University of Kwazulu Natal in Durban, South Africa. And although from his short CV saying that he is a chemical engineer, then spent his career on the industrial wastewater and treating the wastewater, industrial wastewater, but now is currently he is the head of the pollution research group, and they now in this world to be one of the prominent person working on the sanitation. So that the quote is sanitation is dignity. So that one is the big funding recently, of course, from the Bill and Melinda Gates Foundation. You know that Bill Gates is one of the richest men in the world. So that Chris has been, I think, having some project, a number of projects funded by the Bill and the Melinda Gates Foundation. So I think that's the introduction of Professor Chris Buckley. So I just call him Chris. So I think, Chris, you would like to control by yourself, or will help by Adina?
Let me see if I can do it.
Okay.
I've got to learn to do it properly. So let's see how we go. So I should now take over sharing of the screen, should I?
Yes.
Right, here we go.
Okay.
Right, is my
great.
screen shared?
Yeah, great.
Okay, can I start?
Yes, please, Chris.
Right. Good afternoon, everyone, and congratulations to everyone at ITB on 100 years of excellent service to the world. And I hope your next 100 years will be equally successful.
Okay, thank you very much.
Right. I'm going to give you a presentation today, which is going to be based on my experiences from Africa, from South Africa, which is where I have lived for the past 65 years. So although I have visited Indonesia on a number of occasions, my knowledge of Indonesia is not that great. So it will be from the perspective of the country where I'm living and working. It was mentioned that we have some interaction with the Bill and Melinda Gates Foundation. Yes, we run the engineering field testing platform for the Reinvented Toilets Challenge. So in 2011, there was the challenge of reinventing the toilet, and those successful toilets that moved through to the prototype stage had the opportunity to field test their toilets in a real situation, because many of the countries where these toilets had been developed, they were not easy to get on-site sanitation or to actually get hold of feces to do experimental work. So we've had a total of 17 different prototypes coming to Durban, and we've found appropriate places for them, be it a household level, be it the lab, or be it where we've had a community ablution block, to be able to provide these developers with a realistic opportunity to test their technologies. So that is some of the types of opportunities we've had. I also just point out that we are very much funded by the South African Water Research Commission. We've had funding from them for the last 40 odd years, and we have extremely close relations with the Econom municipality, which is the municipality in Durban, and it allows us the opportunity of working with them and evaluating and testing and supporting their sanitation outreach. So without those that support, we wouldn't be able to have half the potential opportunity that we've had. And of course, it is the Pollution Research Group. We're a whole group of people, and it's important to understand that everything that I'm saying has been developed in conjunction with the group over many years. Right, so with that, let me let me move on to my next slide. So what am I going to be speaking about? I'm going to be very briefly, I think we all understand sanitation developing countries, just briefly introduce that. Then I'm going to talk about the planetary boundaries. So that's the boundaries of the Earth. Then a little bit on circular economies and what that implication has for appropriate technology for wastewater treatment. Then I'll move on to the sources of nitrogen and phosphorus, which we will have seen as being one of the major constraints on the planetary boundaries. And then how one deals with nitrogen and phosphorus in conventional wastewater treatments. Then Dewats, which is a technology I think which is quite well known in Indonesia. How does Dewats manage nitrogen and phosphorus? Similarly, how is nitrogen and phosphorus managed in conventional wastewater treatment? Then I'm going to move on to urine separation and urine separation pedestals and why I think there's been a major breakthrough there. Then what can we do with urine? And then finally, I'll end up with a bit of a case study and a prognosis for the future from Durban. Right. So with that, let us move on to the next slide, which would be sanitation in developing countries. Now, I'm sure you're all very familiar with this slide, and so you're over here, I'm down over here, and sanitation situation in Southeast Asia is very much better than it is in Southern Africa, and so you're in a far better position than we are. But I think we can still take the lessons from the future. But we certainly have a long way to go before we sort of have a situation like we see up here. But do we actually want to go into that sort of way, or we've got an opportunity of doing things differently and hopefully better? So moving on then to the next slide. Here we see the planetary boundaries. And the important thing here is the, sorry, I just get this laser printer working. There. Okay. So here we see the various boundaries. We've got novel entities. We've got stratospheric ozone, atmospheric aerosols, ocean acidification, biogeochemical flows. And here you can see phosphorus and nitrogen. There we have the limits of the globe. And there we see where we are going beyond the limits of what the planet can take. Freshwater use, land systems, biosphere integrity, climate change. So you see that majority of the things we're within the red or the yellow, but however this biogeochemical flows, we are way out of balance. We are way beyond using our the amount that the planet is able to sustain ourselves. And where do we get where does the nitrogen and phosphorus come from? It's drinking water. Well, it affects our drinking water, air quality, eutrophication, hypoxia, and climate change, which I'm sure is familiar to all of you. And where does the nitrogen pollution come from? Agriculture, industry, and going to the bathroom. In other words, sanitation wastes. So let us go a little further into it and see where we can go. And this will now introduce the concept of the circular economy. Now, I'm sure this too is not new to you. The linear economy, the take, make, use, dispose, pollute model, which has been of great benefit to all our development over the last century or so, has really come to, we're seeing the pollution, we're seeing the buildup of material which is in the wrong place, energy which is displaced. And so that brings us to the circular economy, which is where we have the full cycle of where we make, use it, reuse it, remake it, and then recycle it. So this is, and I'm sure we've all been looking at different aspects of this. This is not new to people in the environmental field, environmental engineering, but how can we actually think about it and apply it in our circumstances? And what we have to understand is that there actually, there was the Millennium Development Goals, there was the Sustainable Development Goals. Somewhere lurking around there was also the paradigm of the waste minimization, knapsack economy, all of these sorts of different philosophies. And in a way, they've all come together to give us the circular type of movement. So you've got the circular nutrient economy, the circular economy in general, and we've come onto the circular sanitation economy. So if we move on then to the principles of the circular economy, is we have our normal linear system where we got the parts manufacture, product manufacture, service provision, collection, and then it would then go to the environment. But what we can look at in the circular economy is we start seeing a whole series of loops. It's not just one recycle loop. There are many little loops. There's a smaller loop, bigger loop going on like that. And this here is the stock. And so that's the non-renewable material. And here we have the renewable material, how that too can be recycled. So what are we talking about? We're talking about the final product here. We could be sharing it and repairing it, and so it has a longer life. We could be maintaining it and rebuilding it, reusing it and redistributing it as either further circle. And here we have a refurbishment or remanufacture of the article coming around like that. So that is the non-renewable and how we're able to recycle them. And then when we've got from the recyclable components, we've got just the consumer themselves can reuse different components. We could take our biochemical feedstocks that can be reused, and we could extract from whatever we produced new biochemical feedstocks, which could be made into biogas, could go through the biosphere for regeneration, could go to agriculture for farming. So we have these various loops around here. So is this appropriate to sanitation, and how can we think about it as sanitation in the circular economy? Oops, there we go. So let us now think about the nutrients and the nitrogen and phosphorus. Where actually do we find it in sanitation, in human excreta? So what we see here is we've got the nutrients, nitrogen, phosphorus, potassium, sulfur, boron, calcium, magnesium, and iron. These are all nutrients which are in wastewater. And then you've also got some pharmaceutical residuals and things like that. And the urine components, you see the fraction or the proportion. The nitrogen is very definitely, the majority of it is in the urine, phosphorus, potassium, and so we go down, sulfur, boron, calcium, not so much, magnesium, not so much, iron, not so much. So we see that if we are focusing on nitrogen and phosphorus, which is what we want to focus on, we want to focus on nitrogen and phosphorus, it becomes important that we consider the urine and as opposed to the feces and the combined wastewater. So how are we able to do something like that? How do we normally do it? What is the normal way in which we deal with that material? Let us look at the conventional wastewater treatment first. So here we see the history of conventional wastewater treatment, let's say from the 1950s through to the 2020s. That activated sludge was initially there to remove the COD in order to oxidize the ammonia to nitrate, so that we didn't have fish deaths and that we wouldn't have rivers going anoxic. Then we needed nitrification, to get even more lower ammonia levels. Then there was denitrification was introduced to take the nitrate ammonia and the total nitrogen out. Then we had the aerobic and anoxic systems for phosphorus removal. And now we started having some sort of things with absorption and oxidation, maybe membrane processes down here to remove the chemicals of environmental concern, the micropollutants. So we took a process and we started adding on little bits to it, adding on, adding on, adding on. At times, we realized that isn't it time to actually have a redesign of what we're doing? Do we really have to continue doing it the same way and just adding another step onto it here to be able to manage the waste from here? And is it actually appropriate for a developing country to have all of these energy intensive processes as we come down here? And each one of these processes makes biomass, makes sludge. And we find that sludge, the management of sludge is frequently the most expensive part of the operation of a conventional wastewater treatment works. And the Western way of having flushing toilets, is that actually the best way of having a sanitation system? So I can't speak for very much experience with these kind of wastewater treatment plants in Indonesia. So my experience is either South Africa or the Northern Hemisphere, certainly not an Indonesian experience down here. So I can't comment any further to the appropriateness of that in Indonesia. I am a lot more familiar with the Dewats and Borda and the Dewats system. Spent quite a number of years working with Borda and have seen many Dewats plants in Indonesia. I've had a number of master students there. So the Dewats, as you know, it's that gap between conventional wastewater treatment where you can have a large system. It's where you are smaller, sort of between the household level and the community type level, the community ablution blocks, which first time I came across them was in Yogyakarta, probably, I would think it would have been about 12 years ago when I first went to Yogyakarta. So this is a system, it does work, but what does it actually remove? It's very good at removing COD, it removes the COD, it takes suspended solids out. But what it does is it takes the urea in the urine turns to ammonia, and the proteins in the fecal material turns to ammonia. So you end up with the nutrients in the treated wastewater. If it goes over a constructed wetland, you could denitrify, or you could nitrify the urine, and if you had a horizontal flow constructed wetland, you could denitrify it. But they're all large area processes. They're not necessarily very good because you do need to have biodegradable COD there, which then introduces pathogens once again. So the system itself is very good for removing settleable solids and COD, but not so good, and it doesn't really work for the nitrogen and phosphorus. So what to do? Well, let us now move on a little bit to the circular toilet economy. This is an organization known as the Toilet Board Coalition, and they have this visualization of how they would see the circular toilet economy. What is very interesting about the circular toilet economy is that this is all driven by private enterprise. The big companies in the world, manufacturers, are all seeing that their markets, their resources are going to come from the toilet. They see the toilet and the toilet economy as being a source of raw material for them and for their manufacturing processes. So I urge you to go and have a look at their websites. They had a very successful meeting last year in India, and it certainly it's taking off in India and many other countries, the concept of the circular sanitation or circular toilet economy. So we know that the urine and the feces are excreted separately from the body. Current urine separation pedestals are inconvenient, to say the least. They don't suit our lifestyle. Now, there's an organization called EOOS. It's a design organization. They make furniture, design furniture for executive suites and very upmarket places. So what does an upmarket furniture and manufacturer do in the toilet design business? Well, they're innovative people. And they came up with this concept which is called the urine trap. And if you've ever tried to pour a cup of tea or pour some milk out of a jug, how frequently do you find the milk or the tea dribbling down the side of the jug or the teapot and dribbling down onto the table? Now that's called the teapot effect. When the surface tension is great and the liquid actually sticks to the side of the container rather than cascading off. So you have the same teapot effect. So here we've depicted the urine coming down into a conventional pedestal type toilet, coming along this sort of platform, and it stays along the edge, and it comes off and comes down because there's an opening at that spot there. So the urine comes down, round, and gets taken off there. Fecal material falls straight down into the conventional pedestal and out. And so you have the flush water coming in here and going out. Now, remember, this was all developed in the Western world, Northern Hemisphere. So large quantities of water, pedestal type, sitting pedestal type toilets, and large amounts of water. Now, is it actually necessary to use those large quantities of water? And I know many of the toilets in Indonesia are pour flush pedestals, and there's a lot more control over the water that's used there, and it's not of this nature. But this is where it was developed, and this is how the concept was developed. The concept was taken further because this was done through the Bill and Melinda Gates Foundation. It was taken a little bit further. It added to it, and I think you're going to have a presentation in a few days' time from Tamarat from AIT, and he's been working on this a lot. You have this solid liquid separator. This particular one is from Sweden, and Tamarat is working on a similar type one. So there what happens is that you can separate the feces from the flush water. So now what you've been able to do is you have the urine, which is the nitrogen and phosphorus and all the other nutrients are here. The fecal material, which is where all the pathogens are, in here. And you've got a lightly soiled flush water, which is like a very light grey water in composition. So from our pedestal, we were actually able to have 3 different streams, which implies we have 3 different pipes that can come from the bathroom. Now, okay, that's very much a chemical engineering diagram. We're human beings. We don't operate quite like that. So what does a urine separating pedestal look like? So here we see what they've called and this is an EOOS drawing, the Indian squat plate. So this is a squat plate type toilet. The urine would come down here, round, and it gets pulled back here. It comes out there, and the flush water and the feces come down here. And we haven't done tests on this type of toilet. We've done tests on the pedestal type toilet, and we find there's between a 70 and 80% recovery of the urine and less than a 20% dilution. So you certainly get most of the urine coming out. And there's not too much dilution through a pour flush, because the higher velocity of the pour flush comes down here faster and it goes over the top. It doesn't creep down. The flow doesn't creep down and come back this way. So we ask ourselves, would you actually want something like that in your house? Is this the sort of thing that you would like? I mean, you don't change your toilet very often, maybe once every 15, 20 years. It's not the sort of thing, so you want to know it's going to be right. So what the Gates Foundation have done is that they actually went to one of the most upmarket sandware manufacturers, and they developed a range of pedestals. And the pedestals that are sold, it's the most upmarket sanitation company in Switzerland, and their pedestals sell for about $1,500 US. Let's put that into context. Certainly in South Africa, we can import Chinese pedestals for $25. $25, $1,500. There's an incredible difference between them. So what is the relevance to developing countries and relevance to poor people? Well, you can buy a range of cars. You could buy a Datsun, let's say, at the bottom end of the range of the cars, or you could buy a Ferrari. Now, everyone knows about Ferraris. Very few people own them, but you see the Ferraris on the front cover of all sorts of prestigious magazines. You don't see that many Datsuns there. So we all aspire to something like a Ferrari, although we are happy to take a Datsun. So here we see some sort of depiction of the squat pedestal in context. So this is a plumbing diagram. So you see the water flow. So this would be in an apartment block. This is the wastewater flow in the apartment block. Here is the pedestal mounted into the floor of the apartment. Back and there we see the bucket. And here we see it maybe more in context. You see, yeah, we see it sort of in the corner of a room. And here we have a drawing or a rendering of the pedestal. And you see that there is a separate U-bend here compared to the U-bend there, which is the odor trap for this would be the fecal and flush water, and this here would be for the urine. So these ceramic pedestals now are available. We've actually got one of these. It's not actually in ceramic in our lab, which we're going to be, if it hadn't been for the lockdown, we would have had it in an appropriate household. This is actually a 3D printed one that we're working on. They're just finalizing some of the design aspects to it. So this would become available on the market relatively soon. So what I'm sharing with you is that this is going to be the emerging way of sanitation. And we're going to think about how do we manage our sanitation like this in the future, and what is the implication for us as sanitation engineers. Right, so now we've got to the stage of being able to separate the urine from the flush water and from the wastewater. What to do with the urine? So, what to do with the urine? So let's just talk a little bit about urine for a moment. When we eat food for energy and for the metabolism of our body. And if we're adults, we've got past the growing stage. So we're not getting any taller, but what we probably are doing is we're getting fatter. So what does that mean? It means that the food we ingest, we excrete, except if we are retaining any energy, when that energy then manifests itself as body fat, which is an increase in mass. So the nutrients we ingest, we are going to excrete. So that means the nitrogen and phosphorus that we ate yesterday, we would be excreting today. The body doesn't accumulate nitrogen, phosphorus, potassium, sulfur, and so on with the other trace metals, or minerals, which are so necessary for our growth or metabolic processes. So the nutrients that were needed to grow the food, we excrete. So in principle, then, we should be able to sustain ourselves by using our excreta to grow our food. Now, the difficulty, of course, is in when we all live in major cities and conurbations like that, the food has to come from much further away, sometimes even from another country. But we could, in principle, start having urban agriculture. We could be having hydroponic type systems. We could be growing more food within the city. So we are, in principle, able to use the nutrients that are in the urine. The pathogens are in the feces. That contains energy, and there's sufficient energy there to actually combust it, or we could do other things with the feces. So in principle, then, we could go from an energy consuming process to an energy generating process. If we had anaerobic digestion for the feces, we could use a lot less water, and we could return the nutrients. So then what could we do with the urine? It could be direct agricultural reuse. So that's if we're talking about relatively rural communities. After some sort of process, well, we could take the urine and reuse it immediately, and this is done frequently in other East Asian countries. I can't speak for Indonesia. There's possibility of using it in urban agriculture. That's not very widespread at the moment, but it's a whole new way of looking at buildings, keeping buildings cool, having plants on the outside of it, the architecture, bringing architects into it. How do we grow vertical walls? Singapore certainly is promoting this in a big way. There's nitrification, where you could have a specific reactor to nitrify the urine. So you're turning the ammonia into nitrate and then concentrating the whole thing. So we have about 5% of the volume. The disadvantage of urine is that very rapidly the urea transforms into ammonia. The ammonia is volatile. We smell it, and frequently the odor, the malodor associated with toilets is due to the ammoniacal smell of the ammonia. So it's difficult to capture all the nutrients in the urine, or the nitrogen, if it remains in the ammonia form. It would be good to be able to keep the urea as urea. Urea is 2 ammonia molecules and 1 carbon dioxide molecule. Urea is a fertilizer, as we know. It's very stable. It's the greatest nitrogen fertilizer by mass that's sold in the world. Very stable, and it comes in small pellets. And the problem with nitrogen fertilizer when applied by the agriculturalists is that plants require nitrogen at different stages in the growing, but for the agriculturalists, it's most convenient to add the fertilizer right at the very beginning while the seeds are in the ground or crops are small. So more than 50% of the ammonia or the nitrogen that's added agriculturally actually gets lost to the atmosphere just because of the cost of putting it. So if we could add nitrogen through the liquid, like in hydroponics, we would have much more control over the agriculture. And lastly, I'm going to talk about direct discharge to a lime bed and reuse. 2 weeks ago, I had the opportunity of, whereas today I'm zooming into Bandung. 3 weeks ago, I zoomed into Sweden. Certainly you can move around the world quickly these days, and it doesn't take too long. I zoomed into Uppsala in Sweden, and I participated in a PhD examination with someone who is working on that, and a little bit more about that in a moment. So there are ways of working with urine, there are ways of beneficially using it, but it's going to need a bit of a rethink as to some of our thoughts on chemistry and how we engineer things. So capturing of urea in lime, the high pH of lime inhibits the urease enzyme, which breaks the urea into ammonia. And so what we could see here is that we would have the excretion, we would have alkali dehydration, where we would dry it. We could transport it, convert it, utilize it into fertilizer, consume it, comes back down. So you see that by reusing the urine, we could bring urine into a circular urine economy or urea economy. And it's a very small proportion of the mass of the solid waste. The system that I'm talking about can increase the nitrogen concentration from about 0.6% to 6%, but retaining 80% of the nitrogen in the urine. And it has the same nutrient density as commercial fertilizer. And so it can be stored, easily transported in bags like fertilizer, and it has been shown to be safe. So let us just delve into it a little bit more and see what some of the chemistry of the process is. So what do we have? We've got urine coming in. Let's say we've got a kilogram of urine. The nitrogen component in there is about 6 grams in 1,000 grams, a litre of urine. We've got about 6 grams of nitrogen in the form of urea. If we had ash or lime in a box, so in other words, the urine went directly into a powder of a powder which would give you a high pH, and you allowed evaporation to take place here. Then you would have water coming off. You'd see that you've got 967 grams of water out of the 973 grams. 967 comes off. And we end up with, and a little bit of nitrogen comes off. And we end up with dried urine coming out. And we've got 4.9 grams of urine. We started with 6 grams. 4.9 coming out. The total mass is 66 grams. Whereas it was 1,000 grams. So it's much more concentrated, and it's 7.4% nitrogen coming out in this, incorporated into this lime powder. So here you see we've got 6%, greater than 6% nitrogen in the end product, 82% yield in the process, and a 94% mass reduction. So now that's something that one can manage, you can take out. So you could see it, for example, adjacent to a toilet pedestal, and we could, on a monthly basis, let's say, it could be replace that cartridge, and it could be sold, and it could be certainly reused. So the high pH, this is where the urease enzyme in the urea gets inhibited. This pathway down here, the pipe here, needs to be short because the urease enzyme is ubiquitous, it is everywhere. So down any piping system, you're going to get a biofilm formed. And so the biofilm down this pipe would actually transform, or the enzyme in it would transform the urea into ammonia, and there'll be a loss. So the trick is to have this pipe here as short as possible and to maintain its cleanliness, or not to have a biological growth on it. So now you see there is actually a process that could go forward for starting to revisit the toilet economy. So I'm now going to just briefly go through a bit of a case study as to our history with Dewats and how we see the way forward. So I'm going to go back a bit to 1997. 1997, we first came across the anaerobic baffled reactor, and we were looking at a textile dye, and we were seeing it as a way of decolorizing textile dye. And one of the pleasant journeys I've had to Bandung was actually to go around textile mills in Bandung to actually look at the textile factories, and that was the Chandra, and that would probably be in the 1990s at some stage. I really don't remember when I first came to Bandung, but it was quite some time ago.
Yeah.
So let's move slowly through it. Do you remember when it was? Yeah.
I think it's 2001 or something. Or I'm
Right.
not really sure.
Thank you. So that was the beginnings, and then so we had these 5-liter reactors like that. Then we had a bigger one that we had at a wastewater treatment works. We thought we could sample it, all the different parts in it. So we had all the anaerobic baffles down through there. And then in 2005, we said, wait a minute, what about informal settlements like this? This is typical informal settlement. There's no sanitation there at all. Could we not have what I learned from Indonesia was the community ablution blocks, and could we not have a community ablution block for this community here and have it treated in an anaerobic baffled reactor? So that was 2005. So anyway, long short of it, we had Joanne Bell, we had Priyodama, we had Zaman Tembu, Kitty Foxon, Sudhir Pillay, Labrador, Hudson. We had all of these people up to 2005, and we eventually 2009 we started digging our first anaerobic baffled reactor. The municipality then started saying, okay, let's try it, let's give it a go, let's see what we could do. So they started building that for us. As you see, it's starting to take shape. We were really excited. This is the first time anyone had actually taken any of our concepts very seriously. So we were really excited about it. It was almost finished. That's what it was like then. And if we look at it now, our constructed wetland is looking good. The anaerobic baffled reactor is looking good. We're getting pretty good stuff. If we look at it from a drone, now we've got moved into the drone era. So if we look at it today, we've got the anaerobic baffled reactor. What you don't see there's a growing tunnel. That was a containerized anaerobic baffled reactor. We took this one, we were replanting the wetlands, so there's not much on the wetlands. And there's a whole agricultural area down there. And we have a fantastic laboratory here and interpretation center there. So a very active site where we were able to do a lot of research, but now what's happened? Oh dear, my PowerPoint's not responding.
You have to escape from the view and then back to the view.
The sharing the view.
No, I mean, just because you are in the view mode, right? So just click the normal view and then back to the show view. So usually.
Okay. In slideshow, that one.
Okay.
No,
you start again. You start again. You. Okay,
I'm sorry about that.
Yeah. Okay. You share again so that.
I've lost you.
Okay, I will share from my.
Okay, if you wouldn't mind doing that.
Yeah. I think you're here. Okay, this one, right?
I need to. Right, let me close that down and go to here. Yeah, that's it. So
Yeah.
we still sit with the problem here of the nitrogen and phosphorus. So if you go to the next slide, please. So what we have is we have our, you can't see my mouse. So if you look down, here we're seeing the performance of the vertical flow constructed wetland. And we've got the different places, the siphon chamber, which is the feed to it. And then we have the effluent. We have a discharge limit, which are the figures in red, and then the percent removal. So those, the ammonia is highlighted in yellow, the nitrate is highlighted in yellow, and the total suspended solids is highlighted in yellow. Those are all the determinants which are not within specification. And they're out by quite a long way. So what could we do about that? That was a major problem. We were having a difficulty in moving forward with this as a procedure or process because we weren't meeting the discharge to river standard. We were able to use the wastewater successfully, of course, in agriculture where the nitrogen and phosphorus is required. But if we wanted to discharge it through to the environment, the receiving environment, it wasn't acceptable. So what could we do? Where do we get to? Okay, the next one, please. So there we see that $1,500 flushing, urine separating flushing pedestal. That's actually in our laboratory. To the right of it, you will actually see some red numbers there. That's the scale where we're actually weighing the urine. So we're seeing how much urine in the flush water so we can see what the yield is. We've got two scales there. We were able to determine the separation, the flush water, and aspects like that. And so now that we realize that there is a pedestal that can do such a thing, we could then consider if the houses had that kind of pedestal or the various topologies which I've mentioned, and that comes in a whole range of topologies. If we had that, we would take the urine out of the wastewater stream. So if we go to the next slide, please. So now you see we've got various scenarios. We've got a scenario where we have wetlands and urine diversion. So we have yeses and nos for wetlands or no wetlands, urine diversion or no urine diversion. And then we see the columns to the right, we see the ammonia, the nitrate and the phosphate, the minimum and the max. And highlighted in yellow is the main point of the whole thing. If we have wetlands and we have urine separation, we would be able to meet all the stringent discharge limits which are in the last line of the table. I don't know how they compare to your discharge limits, but we would be able to meet our discharge limits. And so we would then deal separately with the urine. So if we move to the next slide, please. So what we have is this, there was this informal settlement called Banana City. It was called Banana City because the people were hiding in the banana trees, which was a great place until, as you know, banana trees don't live forever. And so it became an informal settlement, and we have a system of upgrading, in situ upgrading of informal settlements. So this settlement was due to be upgraded, this is going to be happening later this year and next year. And what we see is that the informal settlement is on two sides of a valley, and the valley flows down. So what we see is that the flow of the river or the valley goes from the top of the slide to the bottom of the slide. You've got that white part in the middle, the river line goes down there. And so we would have 2 Dewats plants, 2 constructed wetlands on either side of the banks of the river, and we would have urine separating toilets. So what we have is the first phase, 400 houses are going to be built with urine separating pedestals. The urine is going to be collected separately. We would have about 1.5 cubic meters of urine a day. And then the grey water and the black water, flush water, would go to the Dewats plant and through over the constructed wetlands. So what we then see is that with the partnership with our municipality, we are able to take this envisaging of the urine separation with a pedestal which the user wouldn't even know that there's urine separating taking place. It has no obvious difference. It's all completely oblivious to the user. We don't really have a real use for the urine at the moment, because that use has to be further developed. We've got to look at it from the perspective of the pathogens. We've got to look at it from the perspective of pharmaceutical residues. We certainly know what the pharmaceutical residues are. We have a very high prevalence of HIV/AIDS and antibiotic-resistant TB. So there's a very high usage of pharmaceuticals, which we do know what is there. So we have to work at safe ways. If we add it to the soil agriculturally, will it be all right? What do we grow? We certainly don't want to grow lettuce and leafy crops like that, but we could be growing trees, we could be growing ornamental flowers, at least while the rest of the research is going on. So we've got to this stage, it's very exciting. The pedestals are actually being made locally. They're going to be they're going to be injection molded out of plastic. We've got a 3D printer, which we are doing printing of the prototypes. So these are going to come in at a very much lower cost and has the potential of rolling out all over the place. They flush because we don't have to have the EU types flushing standards. They would have a urine flush on 50 milliliters and a fecal flush of 1.5 liters. So we bring the water consumption way down. So we would have a water consumption of about 3.5 liters per person per day, which would be the water consumption for the flushing system. Right, so let us just move on to the second last slide, please. So what is our research strategies? Our research strategy is really to learn by doing incrementally. We have a very strong partnership with the municipality. So we were able to have early stage technology transfer, and the co-production of knowledge is not just with the municipality. The people, the residents of Banana City co-produce with us. They are part and parcel of this adventure. We have been working in that community for about 2 years with other sanitation systems. They've got to know us, they've got to trust us. So we're quantifying the excreta streams. We've got to the first stage of treatment. We've got to see how that works, and then we'll move to the second stage, which would be how we're going to manage the urine. And then we just carry on incrementally like that. All the time, of course, we come across problems, got to wait, sit, solve them, and move on again. So with that, I'd like to draw my presentation to an end. Just the last slide is some references. I've referenced the Toilet Board Coalition, which is the sanitation of the circular economy. We've got the Our Urine, which came from IVAC and the VUNA project, and we've got Jenna Senecol's nitrogen in ash, which came from Swedish Agricultural University. And so thank you. This is all due to all the various partners and all the various people that the Pollution Research Group has interacted with over the many years we've been in business. Thank you very much. And I'm sure there's some questions. Okay, so I will now, no, I can't stop the presentation. How are we moving from now? Are you hearing me?
Yes, we are hearing you, Professor Buckley. So it's actually Professor Chandra. You may stop
Yes.
sharing the screen now.
Okay, I will give the explanation just briefly before moving on.
Okay.
Some of participant might not really good in English, so I will speak in bahasa Indonesia only a few minutes, Chris. So you may
Thank
take.
you, certainly.
Ya, Bapak Ibu sekalian, jadi yang disampaikan oleh Profesor Chris, jadi intinya tadi banyak hal yang jadi melihat air limbah itu atau limbah manusia itu bukan cuma sekedar limbah saja, ya. Jadi maaf, jadi bukan sekedar menjadi limbah saja. Jadi kita harus melihatnya menjadi sumber daya, ya. Jadi itu yang disampaikan oleh Prof. Buckley, ya. Jadi kalau tadi disampaikan yang bagian ini, N dan P itu sudah melewati batas-batas kemampuan planet ini untuk mendukung kehidupan manusia. Nah, jadi berarti seharusnya N dan P itu bisa kita recovery, nggak dibuang begitu saja karena ada persoalan ke lingkungan yang besar, gitu. Ya, jadi ini yang dikatakan jadi bahwa sebaiknya jadi yang kita lakukan itu adalah linear ekonomi, jadi kita ngambil dari alam langsung kita buang, ya. Jadi ini adalah pendekatan-pendekatan yang yang konvensional yang kita ada itu bagaimana memikirkan menjadi sirkular. Jadi itu yang dibicarakan. Jadi memanfaatkan N dan P. Jadi ini yang dilihat oleh Profesor Chris Buckley. Jadi sebetulnya antara urin dengan feses, jadi nitrogen, fosfor, potasium itu banyak di urin. Jadi kalau kita bisa memisahkan urin dengan feses, maka banyak yang bisa kita recovery dan mengurangi beban terhadap lingkungan. Kira-kira itu yang disampaikan. Jadi ini adalah jenis toiletnya, ya, jenis toilet yang dipakai bagaimana si toilet itu bisa langsung memisahkan urin dan kemudian fesesnya. Ya, jadi itu yang disampaikan. Jadi memisahkan, kalau urin bisa kita pisahkan dengan feses, maka bisa dijadikan sumber daya, dan urin ini bisa sebagai sumber daya, sebagai pupuk tadi, tetapi pemenuhan baku mutu pun menjadi lebih mudah. Ya, tadi sudah disampaikan ini alat-alat ini katanya sekarang ini toilet kayak begini jadi relatif murah, bisa diprint dibuat dari plastik katanya. Tadi sudah sampaikan. Nah, kemudian termasuk tadi contoh-contoh ini adalah saya berkaitan dengan bagaimana nitrogennya bisa disampaikan. Jadi ini adalah contoh-contoh. Yang berikutnya adalah tadi disampaikan ini menggunakan anaerobic buffer reactor, ya, digabungkan dengan wetland. Ya, jadi anaerobic buffer reactor digabungkan dengan wetland. Jadi kalau anaerobic saja sudah pasti tidak bisa memenuhi baku mutu, tapi kemudian dicampur dengan wetland. Jadi tadi contoh yang disampaikan, ya. Jadi contoh yang disampaikan oleh Profesor Buckley itu kalau gabungan antara buffer dengan construction wetland tetap nggak bisa memenuhi baku mutu yang dipersyaratkan. Amonia nitrogen 6 itu tidak bisa. Jadi Indonesia itu 10 ya. Ya tadi Pak di Indonesia itu domestik itu 10. Jadi kalau dengan masih dengan konsep wetland itu sekitar 20-an. Jadi tidak bisa. Tetapi kalau tadi menggunakan jadi urinnya dipisahkan, jadi UD ini adalah urine diversion. Jadi urinnya dipisahkan. Nah, jadi kalau menggunakan wetland ya. Jadi tetap jadi kemudian dipisahkan urinnya, maka baku mutu amonia 6 itu bisa dicapai. Jadi bahkan hampir nggak ada ini konsentrasi amonianya. Ya, jadi kira-kira itu yang dibicarakan oleh Profesor Chris Buckley. Jadi tidak menggunakan, jadi memikirkan di luar yang sudah kita ketahui. Mungkin sekarang ke pertanyaan-pertanyaan. Mungkin pertanyaan-pertanyaan saya stopkan dulu share saya.
So perhaps
Silakan,
our
Adina.
committee, would like to share this.
Silakan. So that one is from Arisa. Are there any strategy?
Would you like me to respond to these?
Yes. You can read the Chris.
Yes. Okay. Would you like me to read them out,
Yes.
or should I just respond?
No. I think so, that one already showed to the others, so the other can read all this slide. So the first one is the AD&D strategy of visibility review on UDDT implementation, especially in the built city or the city built in city and houses. That's considering the plumbing, reinforcement, and others. Please, Chris, you may.
Right. So to respond to the first part of the question, I think this requires be more appropriate for a greenfield site for new developments rather than where there's existing infrastructure, because you've already got the system, the sewers, the wastewater treatment works there. Whereas if we're looking at a new construction, new area, new development, it's more appropriate there. If we take the case of Paris, where they're redeveloping part of the city where it was an industrial area and it's going to become offices and apartments, there they don't have the sewers that can manage it. So there they are thinking of going to urine separation.
Yeah.
How to treat the smaller amounts of NMP from the feces, considering lower nutrient uptake in anaerobic treatment. Right, so you do need a certain amount of nutrients going to anaerobic treatment, or if you were having activated sludge, you too would need to have some sort of some nutrients there. And the only 80% of the N and P from the urine is captured, so you do have sufficient nitrogen and phosphorus to maintain biological processes that if you were going to have the conventional biological processes.
Yes. Even you have the urine diversion, some of the urine will go also not 100% recover, right? So the urine will go part to the feces, so that it will be enough, the nutrition. So I think this the second question from the Sri Lestari. So even though I think I remember in the 90s, or you are working also with the textile, wastewater, with the color. So that one is, I think, and also with the small industries. So that one is the question is, in the developing countries, there are a lot of small and medium scale industries. So the wastewater treatment plant is expensive and difficult to maintain. Of course, they're willing to prefer wastewater directly to the environment. And there's a lot of batik industry also in the Purwokerto. Purwokerto is in the center of Java. So the question is, I think you are familiar with that one. How we can change the culture? I mean, probably deal with the small scale industries, and then they are willing to treat the wastewater coming from the home industries. Is there possibility to change the culture of the home industries, do you think? Or how to deal with the small scale industries in your experiences?
Right, it's a societal change. I think that society says that there's, we have got sufficiently wealthy, there's been sufficient development, and we can't stand this amount of pollution. So society will then bring pressure on companies to change if they haven't changed beforehand. So sometimes it takes a major catastrophe to change, steps change in society. We just take, well, COVID. We now have COVID, and we had before that, we had SARS, we had these various pandemics that came through, and that changed a lot of things as to how society worked. We had an outbreak of cholera in Durban in 2000, 2001, and that the realization made the city council realize how important it was for sanitation. And although it might seem to be a private investment, in fact, public health is a public good. That if someone in a poor neighborhood has cholera, they very easily get you could catch it through food chain, through a variety of ways, because we all work in the same city together. So all it needs then is for an outbreak of cholera in an area, and suddenly everyone's going to change because they just have to. Pressure just comes. So change is going to come, and you might as well start thinking about it and plan it and do it at your own pace in the right way, rather than to be forced into doing something at a later stage. So even if you can't make the investment now, you can start thinking about what you would do and how you would do it. So any changes you make to your premises and so on would cater for that.
Yeah. Okay.
So the second question: what type of what technology wastewater treatment? It is cheap, easy to operate. So I was really talking mainly now about domestic wastewater sanitation. For industrial effluents, you want to go. The first step is the waste minimization route, and that was another time I was in Jakarta. We talked about waste minimization clubs. What we have to understand is that much of the pollution from an industry is in fact product which could be sold, or the raw materials of product which could be sold. So before considering any type of wastewater treatment, I would certainly consider looking waste minimization, being more efficient and effective as to how you use your raw materials. And maybe you can get away with having little or no pollution at all.
Yeah. Okay.
I don't know if you'd like to expand on that, because we've been through that.
Ya, jadi Bapak Ibu memang tidak mudah untuk, walaupun Chris ini dulu cukup banyak sekali dulu sebelum tahun 90-an, 90 sampai akhir awal 2000-an bekerja dengan teknologi sederhana yang menangani limbah tekstil. Ya, tapi tadi pertanyaan yang disampaikan oleh Prof. Chris, memang kalau untuk industri skala kecil ini, mungkin yang lebih perlu ditekankan adalah meminimalkan limbah itu untuk terjadi. Jadi waste minimization. Jadi mungkin itu yang perlu ditekankan terlebih dahulu, meminimalkan limbah yang terjadi, ya. Kemudian bahkan bisa saja limbahnya menjadi tidak ada atau minimal sekali. Ya, memang sampai sekarang tidak mudah untuk mendapatkan teknologi yang murah, mudah dijalankan untuk limbah-limbah industri. Itu adalah memang tantangan tersendiri. Ya, things the bottom question is about I think that one is already about the same principle.
Right.
It is like cheaper and easier. So you prefer you suggest to use the waste minimization first before going further, right? Ya, jadi
Absolutely.
Bapak Ibu, jadi memang perlu kita tekankan untuk meminimalkan limbah yang terjadi, ya, untuk agar beban WBTP menjadi lebih rendah. Jadi Profesor Chris tidak bisa menjawab secara langsung yang mudah dan murah itu seperti apa begitu. Mungkin ada lagi, so is there any Adina?
Yes, there are a few more questions, Professor Chandra. Please
Yeah,
wait
please.
for the slide to change.
Okay.
I'm sorry.
Okay. That's one about the cost to use the urine trap system in one home, and what is the benefit that we can get from the system?
Right. As far as I know, the pedestal is not commercially available. They're looking to the commercialization of it. So I think at this stage, I can't tell you the costs, but in principle, it's been developed by the Bill and Melinda Gates Foundation, and they have the universal access policy. So in poor countries, it comes at virtually a cost price. So if one can, I don't know so in principle, it shouldn't have a higher cost than your current ceramic pedestals. It shouldn't cost any more than that, because all the IP has been paid for by the Gates Foundation.
Yeah.
So that's on the cost side. The benefit.
Yeah. I think
the water situation is quite varied in Indonesia, from places where there's lots and lots of water, places where there's very little water. So one of the advantages that you have a flush toilet with less than a usage of 3 liters per person per day for complete flushing. And then when your water consumption is so much less, any treatment and any subsequent infrastructure is that much less. So it means that the infrastructure for providing water and the infrastructure for removing water can be reduced. It's all part of the waste reduction, waste minimization. So I don't think the benefits will be very great directly. But if you were to direct the urine, for example, into the lime bed, there would be a value in the fertilizer, so it would be sort of equivalent. But over a period of a year, it wouldn't be very much. But if you're in an agricultural area, then that fertilizer would be of benefit to the farmers. But so the amount of nutrient you excrete is equivalent to the amount of nutrients that's required to grow your food. So it would mean that a family would be able to have enough fertilizer to sustainably grow the food, their own food requirements. Similarly, if you had 1,000 people, there would be sufficient food from that area to grow food for the 1,000 people without having to import fertilizer.
Okay, so I think the explanation probably we jump to the next question to FE. That one is probably I will just skip one, the green one, but I will just move to the gray one. So that you have mentioned that the urine become dry urine. So that one is it's one in one of the slide. Probably that's FE do not get the idea how to get the dry urine. You can explain.
Okay. Let me explain it a little more in more detail. So if one consider and just think about how the concept arose at the beginning, was in Africa, open fires are used quite widely for cooking. So think of wood from trees with a fire, with a lot of ash, maybe a bit of charcoal. And at the end of the day, the people found that if they were to urinate on that ash, it put the fire out at night. And secondly, it never smelt at all. Whereas if people were urinating some other area, the ammoniacal smell would be. And so that got the chemists thinking, and it was an ash bed, a bed of ash or a bed of lime, because you just need that high pH. You want to be above 12.5. So you have a powder of lime or of ash or mixture, and if the urine was to go into that, it would end up with a bit of a paste. But if the bed is sufficiently big, that urine would evaporate, and you would then end up with what was wet lime would become dry once again, and that's what I mean by dried urine. And the high pH would ensure that the urea remained as urea and didn't turn into ammonia and wouldn't be lost. So all the salts that were in the urine would remain, and the water that was associated with the urine would have evaporated from the large surface area of the lime bed.
Yeah, I think I have to explain this one in bahasa.
Okay.
Ya, jadi Bapak Ibu, jadi dried urine itu yang dimas. Jadi kan kalau kita urin kita maksudnya ke arang begitu kan terdiserap begitu ya. Nah ini idenya kira-kira gitu. Jadi urinnya dikontakkan dengan kapur, ya. Jadi urin tersebut dikontakkan tadi kan ada wadahnya, di dalamnya itu ada kapur. Maka urin itu akan diserap oleh kapur. Nah urin itu kan urea. Nah kalau pada pH yang basah seperti itu, maka ureanya akan tertangkap. Jadi tidak akan terputus menjadi amonia kalau tidak terdegradasi menjadi amonia. Nah, jadi ureanya terperangkap di dalam lime-nya, di dalam kapur. Nah, itu yang dipakai, dan itu kan menjadi dried urine. Jadi kapur berserta urin di situ. Jadi nitrogen jadi pupuk gitu, karena ada kandungan nitrogennya. Kira-kira itu yang tadi disampaikan oleh Prof. Chris. So the next question is the red one. Is there any possibility the virus, if you use the urine-based fertilizer, that the virus, a COVID virus, will be there? Or do you have any knowledge on that? The potential extension.
Well, I think at this stage there's a lot of knowledge lacking about the life cycle or the transmission of the COVID virus.
Yeah.
The very high pH. Well, okay, so it depends on the urine itself. Firstly, as far as I know, there has been no evidence that the virus is present in urine. Mm-hmm. Secondly, at this stage, we wouldn't suggest that urine is used for any food-based product without appropriate testing. And certainly, because of the presence of pharmaceuticals and other chemicals of environmental concern. But the different types of urine treatment that are being practiced, for example, for the urine process, there it goes through a high temperature process through the distillation process, so that would have inactivated all viruses. The very high pH of the lime, if it was in the fertilizer-based process, it too would have deactivated pathogens and viruses. The standard way of dealing with fecal sludge in emergency situations is in fact to add lime to it, and that's a well-known and well-accepted way of making safe excreta. So it is something to be aware of, and it's something to keep an eye on, but at this stage I don't see it as being a major threat. I think it is manageable.
Okay, thank you. So that one is now back to the green one. So choosing between the centralized system with the on-site system, how probably what is your opinion on the decentralized system as Dewats, and with the on-site system also has been developed? What is advantages and disadvantages between both systems, if you compare?
That is a very difficult question for me to answer, because it's been probably 8 years since I was last in Indonesia, and I actually can't quite picture what you mean, the context. I think all of these things, context is very important. So I don't feel that I'm an appropriate person to answer that question.
Yeah. Okay, thank you, Chris. So that one is but in this South Africa, as you mentioned, that one is the Dewats system is decentralized system, but on-site system is still on-site treatment is still practices, right?
Oh yes, definitely. There are many VIP toilets, ventilated and improved pit latrines, and there are also urine separating pedestals, which are freestanding as well. So the number of Dewats plants in South Africa is 1. So it's hardly a wide. It's only our 1 and 2 or 3 more that are being built now. So it's not widely used at all in South Africa.
Okay. I think Adina, I think there is still a few minutes.
Yes, Professor Chandra, there are 5 minutes left. So perhaps here we have already displayed some more questions.
The question for Usman, I think that one regarding the pathogen protozoa after we store it in some time or some certain time.
Right. So there's been a lot of work being done on that. If you have urine, and now I'm just taking urine and putting it into a container. In tropical climates, there we use the fact that the urea decomposes into ammonia, the pH goes up, and ammonia itself is a very strong disinfectant. And so if you have ambient temperatures around 20 degrees Celsius, then about 2 months worth of storage. So if you just seal off the tank for 2 months, you'll find that the pathogens, including Ascaris eggs, will all be deactivated. So just storage of urine, degraded urine to ammonia, will be sufficient to ensure it becomes safe to handle.
Yes. Okay, I think the last one about the principle of the separation in the EOOS, so that you can separate the urine and then the feces. What is the principle of separation? Separation principle.
It is a simple hydrodynamics. It's the flow. Possibly if we go back to that teapot analogy, think maybe a coffee pot is more appropriate. If you had a teapot and you poured the tea out of the teapot or the milk out of a milk jug slowly, the liquid doesn't pour directly into the cup. It dribbles down the outside of the teapot. Now, what is there a better analogy in Indonesia? Those coffee punch pots.
Yeah.
Possibly, if you could think of a more appropriate Indonesian analogy.
Yeah. Okay, so that probably I will explain later about it. Adines, waktunya udah, his time is up, right?
Yes, Professor Chandra, the time is still 2 minutes left, but perhaps if Professor Buckley wants to give any closing remarks before we close our session for today.
Right. Well, thank you very much for the invitation to speak to you. I've enjoyed it very much. Really what I'm hope to bring across to you is that there are different ways of moving forward, that you're all moving into your next 100 years and see how to do things differently, that you don't do things the same way that you did before. We're all different. The fact that we've had lockdowns and COVID, we've changed our way. We're all sitting at home watching this. We're not in lecture theatres. But change always comes and it brings things along. And I hope that I'm showing you a different way of looking at the sanitation systems that would bring you into the circular economy and that there is use for the different fecal products. With that, thank you very much. And
thank you.
I've really enjoyed it.
I think I would like to thank you again, Chris. I think I will keep in touch with you. So we'll have another discussion. It will be some time before we can visit each other again. But I'd like to thank you for your time. Thank you very much. Thank you.
Thank you very much, Professor.
Thank you, Ada.
Thank you. Bye-bye. Adina, silakan.
Iya, mungkin untuk sesi selanjutnya, karena sudah pukul 14.30 waktu Indonesia Barat, dipersilahkan kepada Alifah untuk mengambil alih sesi, mungkin agar bisa dilanjutkan ke sesi berikutnya. Saya mohon undur diri, terima kasih.
Yang di webinar, yang di YouTube, dari YouTube dulu mungkin ya?